Hello, peoples. So today I was thinking about states of matter bonds. After doing that forces video and looking at that, I thought I would look at like the different bonds, and especially, actually, let's go to the first thing. Okay, so here's a little neutron, which is two photons trapped over their own gravity. One of these photons will decay. It will decay with the positive going inward because that's the way this world side of the manifold works. The negative side will go outwards and become the electron shell. And so here's a neutron, and here's another neutron, and here's another neutron. Let's say this is in a neutron star. 4 claps. Okay, so we got a bunch of neutrons. And they're really, 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 really close. You know? These things are packed in there. Okay, but there's still neutrons, which means it's sort of like there would be the photon shell, and then there's a gap, maybe the same way 1 over 137, sort of where you have 2 electrons, but 2 electrons can't share exactly the same shell. They have to be spin unaligned, and there's a little tiny gap there, and it might be exactly the same way. It would make sense with the photons. It's like they can't be right on top of each other because then they'd be sharing the same space and they might interfere with each other's fields. So instead, by giving them a tiny little gap, you temporarily, I guess, rectify that situation. Okay. So here we go. Now remember, right, all of these are photons trapped over their own gravity. That's where we get mass from. And then suddenly we have the next phase change, okay, where these end up being pushed so close together that they actually touch. And see, whereas before this was this photon, and this is the only frequency this photon had because it was trapped over its own gravity. Once they touch and become the vacuum energy, all the photons in a way are like all frequencies at the same time, because so this is just swirliness. Photons going, it's all frequencies of photons all the time, because there's no particular frequency of photon. It is photon. It's a layer of pure photons so close to each other they're all wrapped around each other. Now, of course, to us, they're spinning in this plane. My friend actually just asked me about this because I indicated a little bit of a tip to my skyrmions, as he called them, and I was like, yeah, but that's just so you can tell. If it's a perfectly flat skyrmion, there's a handedness, but there's no evidentiary handedness because it's flat. When you've got a neutrino, then all of a sudden you've got this wobble to this, which makes sometimes this axis, because there's 3 axes going, this is the only one I'm showing right now, tips up and becomes more evident, and this is the charge axis, which goes down, and then this axis, which is the magnetic axis, let's say, or whatever, this is the electrical, this is the magnetic, then this one tops up because it's a wobbling, like the axis is wobbling. Here's my little model. Oh yeah, there it is. So let's just say for right now, red. It's spinning like this, right? See, the red is just red to us all the time. Red is just red. But then, if this starts going like this, then all of a sudden it's like, wait, that blue is at the same point as where the red is now. And it's like, ow, and now the yellow is up where the red should be. So a neutrino would be a very wobbling skyrmion. An electron would be a skyrmion that's tipped completely on its side, so it's completely just inflow to our side, outflow from the other side, and vice versa for the other charges. Okay, but this is the thing, that as soon as the neutrons invert, that's the moment they become the vacuum energy. That's the moment that they bond with each other and become a singular thing. A singular thing is the vacuum energy. Really, it's the universe. This universe is a singular thing. But this is the evident. This is like what is acting like a singular thing, which is what was fascinating about, I just read an article about the fact that apparently anti-helium disappears. Anti-helium and helium are practically seem to act very the same when they are supercooled to ridiculous levels. So let's talk about the chemical bonds in a goofy, my kind of way of just talking about them. Okay, so here's an atom. Ionic bond, here's an atom, here's a charge thing. This is negative charge, here's an atom, probably because it's a composite atom, 2 parts. You know, for some reason its charge is here, so this has got like, this doesn't have, all the negative is concentrated down here, so this has got a bit of positiveness, so this connects. So I consider ionic bonds are like people you know because you have a common interest. So it holds you together, it binds you together, but it's not really super strong. You know, if you inserted the right charge, you could bust this up. And it wouldn't take that much. You'd only have to have, basically you have to walk up to somebody with a different interest that they're also interested in equally. Okay, covalent bond, on the other hand, is more like a family, I would say. Because what you do is you have sharing across it there, and a much stronger bond here. It would take a lot more to break up this bond. You could, but it would take a lot more. A lot of times what you'll have is, this will be a covalent bond, you'll have another thing like this, another family, molecule, covalently bonded, and another one, and then their ionic bonds, their various interests and needs will bring them together into a larger mass. But these individual parts could be blown away fairly easily. Those bonds are not as strong as this bond here, because this is like filial bond, paternal bond. It's a very strong bond. I'm not saying that everybody who's filial or maternal or paternal has great bonds with their peoples, but I'm just saying that's what we call it. Okay, it's a very strong bond. And then the metallic bond, which is, there's van der Waals too, but the metallic is interesting because that's like a crazy cult or an army, right? Because you have all of these identical atoms. And they are so completely collectivist that this atom is going to share electrons with this atom, all the stuff, all their charge, all their, you know, stuff is being shared amongst the totality of this complete unit. It's like Spartans or something like that, you know? It's a collectivist. And thus, when you input a disruption, a charge, this doesn't break up because it just distributes the problem, the charge, throughout the entire corpus. Whereas Because an ionic bond, it would just be all happening to that because that's a thing. Or if it was a bunch of them, it would bust them apart because all of a sudden the charge would be overcome by the charge bonding thing. This is like, it's sort of like covalent all over the place. This is collectivism. Be careful. Yeah, so this is my politics and chemical bonding and how the vacuum energy gets manifest all in one.